Okay, so let's take a look at number 16 on our sample final. This is a problem on optimization. It states a rectangular poster is to have an area of 100 inches squared with 1 inch margins on the right and left sides and 2-inch margins at the top and bottom. And what we want to do is find the dimensions of this rectangular poster with the largest printed area. So what we need to do in this problem is first create a sketch. From that sketch, we will be able to create or extract two equations. One of those equations are going to be the objective or primary equation, and the second equation is our secondary or constraint equation. So let's make our sketch. So what I'm going to do is I'm going to sketch our rectangular poster so that way it can look like pretty much a printing paper where the longer sides are going to be vertical and the shorter sides are going to be horizontal. So it looks something like this. So for my longer sides, since we're dealing with a rectangle, I can label it as L, and I can label the shorter side my width, W. So what do we know about this rectangular poster? Well, if you want to compute the area of this rectangular poster, area is going to equal to length times width, L times W. Well, it's given that this rectangular poster must have an area of 100 inches squared. So area equals 100. So that implies that the area of your rectangular poster is going to be 100, which is equal to the values of L times W. So this equation here will represent basically our secondary or our constraint equation. So I'm going to label it as my constraint. And now what we need to do is figure out what would basically be my primary equation. Well, if you want to figure out the primary equation, the rest of the problem is the key to determine it. If you notice, it states that for your printed area of this rectangular poster, it's going to come with 1-inch margins on the right and left. So we're going to have, basically we're taking away 1 inch from the left and the right of your shorter side, right? So taking away 1 inch here, taking away 1 inch there, and we're also going to be taking away 2 inches from the top and the bottom. So here's going to be 2 inches from the top and 2 inches from the bottom. So roughly speaking, this is what your poster will look like. This is what your printed area will look like. So I'm going to label it P. For printed area. And what we want to do is figure out the dimensions of our rectangular poster, meaning the bigger poster or the bigger rectangle, such that we can maximize this area of the printed piece. Well, if you notice, if this is your rectangle, your rectangular poster, and this is your printed area, then there's a relation between the two, right? If you notice, for our objective equation here, the area of this printed piece, I'm going to call it A, or AP, just for area of the printed piece, it has a relation with the length and the width of your rectangular poster. Observe. If you notice, for the longer sides, let's begin with that. The longer sides of your printed area has a relation with the longer side of your rectangular poster. The only difference between the two sides is that we're taking away 2 inches from the bottom and 2 inches from the top. So that area, in terms of its, I'm sorry, not the area, the measurement of the longer side is going to be L minus 4. right? Because of the fact that if you take away 2 inches from the top and 2 inches from the bottom, then you're taking away a total of 4 inches. Now, for your width of your printed area, it has a relation with W, the shorter side of your rectangle, and because we're taking away 1 inch from the left and right, then we can rewrite its width as W minus 2, right? Because if you take away 1 inch from the left and right, that's a total of 2 inches. So its width of the shorter, the width of basically the printed piece of your rectangular poster is going to be W minus 2. Okay, so here's our objective equation. Now what we need to do is rewrite the area of your printed piece or your objective equation in a single variable. And that's where your constraint equation comes into play. If you notice, your constraint was given to be 100 equals L times W. So you can rewrite this where basically you isolate L or W on one side of the equation. If you do, you can rewrite this as, if I want to rewrite this where I isolate L, then it's going to be L equals 100 over W. So this 100 over W, I can replace it now into my objective equation. So AP, meaning the area of the printed piece, is going to equal to 100 over W minus 4 times W minus 2. And now I can go ahead and FOIL this out, and then I'll be able to apply my calculus steps. So this area of your printed piece is going to equal to, well, if I take 100 over W and I multiply it by W minus 2, I'll get 100, right? The W's will cancel, and then 100 over W times negative 2 is negative 200 over W. Now I can take negative 4, multiply it by W, that will give me negative 4W, and then take negative 4 times negative 2, that will give me a positive 8. Now I can combine any like terms such as 108, 100 plus 8, which is 108. So the area of your printed piece is going to be 100 minus 200 over W minus 4W. So there is my objective equation. Now what we want to do with the objective equation is basically apply now our calculus. Because it's in a single variable, I can compute its derivative. So here we go. So I'm going to begin the calculus stuff. I'm going to take the derivative of AP, so A prime of P, meaning the area, the derivative of the area of your printed piece is going to be the following. Well, the derivative of 100 is 0. Now, for negative 200 over W, I can rewrite that as negative 200 W to the negative first power. And now, if I apply my power rule, negative 200 times negative 1, that will be 200 W raised to the power of negative 2. And now take the derivative of negative 4W, which is negative 4. So, just rewriting our derivative, it's going to be 200 over W squared minus 4. Now, notice that again, if you want to talk about your feasible domain of your area of your printed piece, notice that W must be a positive number. Since you're dealing with area, you can't have W to be 0 or negative. So we can go ahead in this case and set our derivative equal to 0. We don't have to worry about where the derivative is undefined. So if we set this equal to 0, I'm going to solve for W and then verify that W is indeed going to be a max. So what we're going to have is the following. We're going to have 200 over W squared minus 4 equals to 0. I'm going to add 4 on both sides. So 200 over W squared is equal to 4. Now I can rewrite 4 as 4 over 1. And now I'll be able to cross multiply. So what we'll get is the following. W squared times 4 is going to be 4W squared. 200 times 1 is 200. I can divide by 4 on both sides. If we do, we're going to get W squared is equal to 50. And if we take the square root of 50, we're going to get that W is going to equal to the square root of 50. Now you can simplify this, but I'm just going to leave it alone for right now. So W is going to equal to the square root of 50 inches. Now what we want to do is verify that this is indeed going to be a maximum. So to verify that this is a maximum, we compute our second derivative just to verify it. If it is the maximum, then I can be able to plug it into my constraint equation and solve for L. So just make a note. A double prime of P, meaning the second derivative of the area of the printed piece. If I compute it, then I need to take the derivative of the first derivative. So this will give me the following. I can bring the negative 2 down, so negative 2 times 200 is negative 400. W raised to the power of negative 3. Well, this is equivalent to negative 400 over W to the third power. Now, because W is square root of 50, which is a positive number, when I plug that in for W, we're going to have negative 400, negative number, divided by a positive number. So this is going to equal to negative over positive, which is going to be equal to negative. So by the second derivative test, since when we plug in the value of W into our second derivative, it's going to be less than 0, therefore it is a max. So I can just write that A double prime of P, which was going to be the square root of 50, this is going to be less than 0, hence it's a max. So since W is equal to the square root of 50 is a max. So now that I know what the value of W is, I can just find the value of L, and that will conclude this problem. So since W is equal to the square root of 50, it follows that L, your length, remember, L was equal to 100 over W. So L is going to equal to 100 over the square root of 50 inches, and therefore you found the dimensions of your rectangular poster that will maximize the area of the printed piece. So your final answer is this. Your dimensions are going to be the square root of 50 inches by the square 100 over the square root of 50 inches. And that again is the dimension of the rectangular poster that will maximize or find the largest printed area. Now if you wanted to find the largest printed area, you would have had to plug in these two values back into your objective equation and then solve. But the problem didn't ask you for that, it just asks you for the values of L and W. And that's it with problem number 16.